Tonight, we're going to explore one of the most confusing contradictions in the universe. Space is cold. Brutally, unimaginably cold. The temperature of empty space sits at about -454 degrees Fahrenheit. That's just a few degrees above absolute zero, the coldest temperature physically possible. And yet, floating in that frozen void are stars. Billions upon billions of them. Each one a nuclear furnace burning at millions of degrees. Our sun's core reaches about 27 million degrees Fahrenheit. The surface, the coolest part we can see, still blazes at 10,000 degrees. So, how can space be so cold when it's filled with objects so hot? By the end of tonight, you're going to see that this isn't just about distance or emptiness. It's about something far stranger that changes what you think temperature actually is. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what most people think they understand about temperature. You've been told your whole life that heat rises, that hot things warm up cold things, that if you stand near a fire, you get warm. All of this is true, but it's incomplete. It describes heat transfer on Earth, in our atmosphere, under very specific conditions that don't apply to most of the universe. The problem is, we build our intuition about temperature from our everyday experience. We live at the bottom of an ocean of air. Every experience you've ever had with heat and cold has occurred within this medium. You've never truly experienced the temperature of space because you've never been in a true vacuum. Even the best vacuum chambers on Earth still contain some air molecules. Not many, but enough to make them different from the emptiness between stars. To understand why space is cold, we first need to understand what temperature actually is. And this is where most people's understanding breaks down. Temperature isn't a thing. It's not a substance or a force or a field. Temperature is a measurement of motion. Specifically, it measures the average kinetic energy of particles. When particles move fast, they have high kinetic energy, and we measure that as high temperature. When particles move slowly, they have low kinetic energy, and we measure that as low temperature. At absolute zero, particles would theoretically stop moving entirely. No vibration, no motion, no kinetic energy at all. This is the coldest possible temperature because you can't have less than zero motion. Notice something important here. Temperature is a property of matter, of particles. You need particles to have temperature. A single atom can have kinetic energy, so you could, in principle, assign it a temperature. A collection of atoms, like the air in a room, has a temperature based on the average kinetic energy of all those atoms bouncing around. But what about a region of space with no atoms? What's its temperature? This is where the answer gets strange. Empty space doesn't have a temperature in the traditional sense. Temperature measures particle motion, and empty space has no particles. It's like asking what color the number 7 is. The question doesn't make sense because color is a property of light, not numbers. Temperature is a property of matter, not empty space. But wait, you might say. Scientists tell us space has a temperature. The cosmic microwave background radiation, the afterglow of the Big Bang, gives space this temperature. That's true, but it's measuring something specific. It's measuring the temperature that an object placed in space would eventually reach if it's not near any stars, and if it's only interacting with the background radiation filling the universe. Let me explain what that means. After the Big Bang, the universe was incredibly hot. As it expanded, it cooled. The radiation from that early hot dense state has been stretching and cooling for nearly 14 billion years. Today, that ancient radiation fills all of space. It's everywhere. A faint glow of microwave radiation in every direction. This is the cosmic microwave background. It has a temperature of about 2.7 degrees above absolute zero, or minus 454 degrees Fahrenheit. If you put a thermometer in deep space, far from any stars, it would eventually reach thermal equilibrium with this background radiation. The thermometer would absorb microwave photons from the cosmic background and emit its own radiation until it settled at this temperature. That's what we mean when we say space has a temperature. We're not measuring the temperature of space itself. We're measuring the temperature of the radiation filling space. Or, more precisely, the temperature that an object would reach if it only interacted with that radiation. Now, let's talk about stars. Our Sun is a ball of hydrogen and helium undergoing nuclear fusion. In its core, hydrogen atoms are being crushed together with such force that they fuse into helium, releasing enormous amounts of energy. This process requires temperatures around 27 million degrees Fahrenheit and pressures millions of times greater than Earth's atmosphere. Let me be more specific about what's happening in there. The Sun's core reaches about 27 million degrees Fahrenheit. At this temperature, hydrogen nuclei, which are just single protons, are moving so fast that they can overcome the electromagnetic repulsion between them. Normally, protons repel each other because they're both positively charged. Like charges repel. This electromagnetic force is strong, much stronger than gravity. But at 15 million degrees, the protons are moving so fast that some of them collide with enough energy to get within range of the strong nuclear force. The strong force is one of the four fundamental forces of nature. It's incredibly powerful, but it only works at very short ranges, distances smaller than an atomic nucleus. When two protons get that close, the strong force overwhelms the electromagnetic repulsion and binds them together. This creates a diproton, two protons stuck together. Usually, a diproton is unstable and falls apart immediately. But very occasionally, one of the protons converts into a neutron through a process called beta plus decay. This involves the weak nuclear force. Another fundamental force. The proton emits a positron and a neutrino and becomes a neutron. Now you have a proton and a neutron stuck together. This is deuterium, a heavy isotope of hydrogen. Deuterium is stable. Once it forms, it doesn't fall apart. This is the first step of the proton-proton chain, the fusion reaction that powers the Sun and most other stars. The deuterium nucleus quickly collides with another proton, fusing to form helium-3, an isotope of helium with two protons and one neutron. This releases energy in the form of a gamma-ray photon. Finally, two helium-3 nuclei collide and fuse, forming helium-4, the common stable isotope of helium, and releasing two protons back into the mix. The net result of this process is that four protons fuse to create one helium, four nucleus, two neutrinos, two positrons, and several gamma-ray photons. The helium-4 nucleus weighs slightly less than the four protons that went into making it, about 0.7% less. That missing mass doesn't disappear. It's converted into energy according to Einstein's famous equation, E equals mc squared. Energy equals mass times the speed of light squared. The speed of light is a huge number, about 300 million meters per second. Square that, and you get 90 trillion, or 90 times 10 to the power of 15. So even a tiny amount of mass converts into an enormous amount of energy. In the Sun's core, about 600 million tons of hydrogen fuses into helium every second. That's 600 million tons per second, continuously, day and night, for billions of years. About 4 million tons of that mass is converted directly into energy every second. 4 million tons of matter turning into pure energy. That energy is released as gamma rays, extremely high-energy photons. These gamma rays stream outward from the core, carrying the energy with them. But they don't just fly straight out. The Sun is dense. The core has a density about 150 times that of water. It's packed with atomic nuclei and free electrons. The gamma-ray photons can't travel far before they hit something. When a gamma-ray photon hits an electron, it gets absorbed. The electron's energy increases. Then the electron re-emits a photon, usually at a lower energy than the gamma-ray it absorbed. This photon travels a short distance and gets absorbed by another electron. That electron re-emits another photon, and the process repeats. Over and over and over. Each photon gets absorbed and re-emitted millions of times as it works its way from the core toward the surface. Each time, it loses a bit of energy, shifting to longer wavelengths. Gamma rays become X-rays. X-rays become ultraviolet. Ultraviolet becomes visible light and infrared. This process takes a long time. A photon created in the core might take 10,000 years or more to reach the surface. It's traveling at the speed of light, but it's taking such a zigzag path, being absorbed and re-emitted constantly, that its net progress outward is incredibly slow. This is called a random walk, and it's one of the reasons the Sun doesn't explode. The energy generated in the core is released slowly, over thousands of years, giving the Sun time to adjust and maintain equilibrium. Eventually, the photon reaches the outer layers of the Sun, the convection zone. Here, the density is low enough that photons can travel farther between collisions. Heat is transported more by convection than by radiation. Hot plasma rises, cool plasma sinks, creating massive convection cells that churn the outer third of the Sun's interior. These convection cells are enormous, some as large as Earth. They carry energy from the interior to the surface, where it's finally released as light and heat. The surface layer of the Sun, the photosphere, is where the density drops low enough that photons can escape into space. This is what we see when we look at the Sun. The photosphere has a temperature of about 10,000 degrees Fahrenheit, much cooler than the core, but still hot enough to emit visible light. The photosphere is not a solid surface. The Sun is a ball of gas with no solid parts. The photosphere is just the layer where the gas becomes thin enough that we can see through it. Below that layer, the Sun is opaque. Above it, the Sun is transparent. From the photosphere, radiation streams outward in all directions at the speed of light. This is sunlight, the electromagnetic radiation we see and feel. It's a mix of wavelengths, ultraviolet, visible light, infrared, with the peak intensity in the visible range. This radiation carries energy, about 3.8 times 10 to the power of 26 watts. That's 3.8, followed by 26 zeros, 380 septillion watts. To put that in perspective, The entire human civilization uses about 18 trillion watts of power. The sun outputs 21 trillion times more energy than all of human civilization uses. Every second. And it's been doing this for about 4.6 billion years. The energy generated in the core works its way outward through the sun's interior. It takes thousands of years for a photon created in the core to reach the surface because it keeps getting absorbed and re-emitted by atoms along the way. Eventually, it reaches the sun's surface, the photosphere. This is the layer we can see. It's the coolest part of the sun, but cool is relative. The photosphere has a temperature of about 10,000 degrees Fahrenheit, hot enough to vaporize any known substance instantly. From the photosphere, radiation streams outward into space. Light, infrared radiation, ultraviolet radiation, all forms of electromagnetic energy radiating outward in all directions. This is how the sun transfers its energy to space. Not through conduction or convection, the mechanisms we're familiar with on Earth, but through radiation. And here's the critical thing to understand. Radiation doesn't require a medium. It can travel through a perfect vacuum. When you stand in sunlight on Earth, you feel warm. That warmth isn't coming from hot air. It's coming directly from electromagnetic radiation emitted by the sun, traveling 93 million miles through the vacuum of space and being absorbed by your skin. Your skin absorbs the radiation and converts it to heat. The atoms in your skin start moving faster. Their kinetic energy increases, and you feel warm. This works on Earth, but Earth has something space doesn't: an atmosphere. Let's talk in detail about the three main mechanisms of heat transfer, because understanding them is crucial to understanding why space behaves the way it does. The first mechanism is conduction. This is heat transfer through direct contact. When you touch a hot stove, heat flows from the stove into your hand through conduction. The atoms in the stove are vibrating rapidly because they're hot. When your hand touches the stove, those vibrating atoms bump into the atoms in your skin. The collisions transfer kinetic energy from the stove atoms to your skin atoms. Your skin atoms start vibrating faster, which means they get hotter. You feel this as heat, and if the stove is hot enough, as pain. Conduction requires physical contact. The atoms of one object must be touching the atoms of another object. In space, this is rare. Objects are far apart. There's nothing between them to conduct heat. A spacecraft near Earth might be bathed in sunlight, but there's no air touching it to conduct that heat away. The only way heat can leave the spacecraft through conduction is if something physically touches it, and in space, nothing does. The second mechanism is convection. This is heat transfer through the movement of fluids, either liquids or gases. When you boil water on a stove, the water at the bottom of the pot heats up first. Hot water is less dense than cold water, so it rises. As it rises, it carries heat with it. Cold water sinks to replace it, creating a circulation pattern called a convection current. This is how heat spreads through the water, not just by conduction from the bottom, but by the movement of the water itself. The same thing happens in Earth's atmosphere. Air, heated by the ground, rises. As it rises, it carries heat upward. Cooler air sinks to replace it. This creates wind and weather patterns, all driven by convection. Convection is incredibly effective at moving heat around. It's why a fan cools you down even if the air temperature doesn't change. The fan moves air across your skin, carrying away the heat your body produces. Without convection, that heat would just sit there, trapped in a thin layer of air around your body. But in space, there's no convection because there's no fluid to move. No air, no water, nothing. A hot object in space can't create a convection current because there's nothing to create the current in. The third mechanism is radiation. This is heat transfer through electromagnetic waves. Every object with a temperature above absolute zero emits electromagnetic radiation. Hot objects emit high-energy radiation, ultraviolet or visible light. Warm objects emit lower-energy radiation, infrared. Cool objects emit very low-energy radiation, microwaves or radio waves. The hotter the object, the more radiation it emits, and the higher the energy of that radiation. This is described by the Stefan-Boltzmann law, which states that the power radiated by an object is proportional to the fourth power of its temperature. Double the temperature, and the radiated power increases by a factor of 16. That's 2 to the fourth power. Triple the temperature, and the radiated power increases by a factor of 81. That's 3 to the fourth power. This is why hot objects glow. The sun, at 10,000 degrees Fahrenheit, emits visible light, lots of it. A piece of metal at 2,000 degrees glows red. A piece of metal at room temperature doesn't glow visibly, but it does emit infrared radiation. You can't see it with your eyes, but an infrared camera can. Everything emits radiation based on its temperature. You're emitting infrared radiation right now. Your body temperature is about 98.6 degrees Fahrenheit, so you emit infrared radiation with a peak wavelength of about 9.4 micrometers. This is invisible to your eyes, but it's there, streaming off your skin in all directions. In Earth's atmosphere, this radiation doesn't travel far before it's absorbed by air molecules or water vapor. But in space, it would travel unimpeded until it hits something. This is the only mechanism of heat transfer that works in a vacuum. Radiation doesn't need a medium. It doesn't need air or water or anything. Electromagnetic waves can travel through empty space, which is why we can see stars that are billions of light years away. Their light, their radiation, crosses the void and reaches us. On Earth, all three mechanisms work together. When you stand in sunlight, you absorb radiation from the sun. Your skin heats up. That heat is conducted into the air immediately around your skin. The air heats up and rises through convection, carrying the heat away. You might also sweat, and the evaporation of sweat cools you through a process that involves all three mechanisms. But in space, only radiation works. When sunlight hits your spacesuit, the suit absorbs radiation and heats up. That heat can't be conducted away because there's no air. It can't be convected away because there's no air. The only way to get rid of it is to radiate it away as infrared radiation. The suit gets hot, starts glowing in infrared, and slowly radiates the heat into space. The problem is, radiation is much slower than conduction or convection at removing heat. This is why spacecraft need active cooling systems. They can't rely on passive radiation alone to dump all the heat they generate. They need pumps and radiators and coolant loops to move heat from inside the spacecraft to large panels designed to radiate it away efficiently. The International Space Station has enormous radiator panels for exactly this reason. They glow brightly in infrared radiating away the heat generated by all the electronics and humans inside the station. Without these radiators, the station would overheat within hours. When sunlight warms your skin then warms the air around it through conduction. Air molecules bump into your skin, pick up energy, and carry it away. You also lose heat through convection, the movement of warm air rising and cool air sinking. And you lose heat through evaporation if you're sweating. Water on your skin absorbs heat as it evaporates, cooling you down. All of these mechanisms require air. In the vacuum of space, none of them work. There are no air molecules to conduct heat away. No convection currents. No evaporation. The only way to transfer heat in a vacuum is through radiation. This has some counterintuitive consequences. Imagine you're floating in space near Earth's orbit, the same distance from the Sun as our planet. One side of your body faces the Sun. The other side faces away. The side facing the Sun is hit by intense solar radiation. It could heat up to about 250 degrees Fahrenheit or more, hot enough to be extremely uncomfortable and eventually damaging. The side facing away from the Sun radiates heat into space, but receives almost no radiation in return, just the faint cosmic microwave background. That side could cool to minus 250 degrees Fahrenheit or colder. You'd have one side baking and one side freezing at the same time. This isn't theoretical. It's exactly what astronauts experience during spacewalks. Their spacesuits have to be engineered to handle these extremes. The suits use multiple layers of insulation, reflective materials, and an active cooling system that circulates water through tubes to remove excess heat from the sun-facing side. Without these systems, an astronaut would cook on one side and freeze on the other within minutes. The Apollo astronauts who walked on the moon dealt with even more extreme conditions. On the lunar surface, with no atmosphere to scatter or absorb sunlight, temperatures in direct sunlight reached about 253 degrees Fahrenheit. In shadow, temperatures dropped to about minus 243 degrees. The moon's surface swings through a temperature range of nearly 500 degrees just by rotating from day to night. Earth doesn't experience these extremes because our atmosphere acts as a buffer. It scatters and absorbs some incoming solar radiation, preventing the surface from getting too hot. It also traps outgoing infrared radiation, preventing the surface from getting too cold at night. The result is a much more moderate temperature range. Even in deserts, where day-night temperature swings are large, they're nothing compared to the moon. A desert might swing from 110 degrees during the day to 40 degrees at night. That's a 70-degree range. The moon swings through nearly 500 degrees, 7 times larger. This is what happens when you have no atmosphere. No buffer between you and the raw radiation of the sun on one side and the cold void of space on the other. This is exactly what happens to spacecraft and satellites. Engineers have to design them to handle these extreme temperature swings. They use reflective materials to deflect solar radiation, insulation to slow heat transfer, and sometimes active cooling systems that pump heat from one part of the spacecraft to another. Without these systems, electronics would overheat on the sun-facing side and freeze on the shaded side. The International Space Station experiences this constantly. It orbits Earth every 90 minutes or so. For about 45 minutes, it's in sunlight, baking at temperatures that can exceed 250 degrees Fahrenheit on sun-facing surfaces. Then it enters Earth's shadow. and those same surfaces can plunge to minus 250 degrees. This happens every 90 minutes, 16 times a day. The station's thermal control system works constantly to manage these temperature swings and keep the interior habitable. Now, let's think about what this means for the question we started with. Why is space cold when stars are hot? Space is cold because there's nothing there to be hot. Temperature is a property of matter. Space, by definition, is the absence of matter. The vacuum between stars contains almost nothing. In interstellar space, the density is about 1 atom per cubic centimeter. That's 1 atom in a volume about the size of a small thimble. On Earth, that same volume contains about 10 to the power of 19 atoms. That's 10 billion atoms. Space is emptier than any vacuum we can create on Earth by a factor of billions. With so few atoms, there's almost nothing to have a temperature. Those few atoms that do exist, the occasional hydrogen or helium atom drifting through space, might actually be moving quite fast. If you measured the kinetic energy of one of those atoms, you might calculate a very high temperature, thousands or even millions of degrees. But that one atom can't transfer much heat to anything else because there's nothing for it to transfer heat to. It's alone in the vast emptiness. If that atom hits a spacecraft, it will transfer a tiny amount of energy, but one atom doesn't carry much energy. You'd need trillions of atoms hitting the spacecraft to transfer any meaningful amount of heat. Stars are hot because they're made of matter. Huge amounts of matter packed densely together. The Sun contains about 2 times 10 to the power of 30 kilograms of matter. That's 2 billion kilograms. All of it squeezed into a ball about 1.4 million kilometers across. In the core, the density is about 150 times the density of water. Atoms are packed so tightly that they can't avoid colliding with each other, fusing together, releasing energy. That energy heats the surrounding matter, which collides with more matter, transferring heat through conduction and convection and radiation. The Sun is hot because it has matter, and that matter is energized by nuclear fusion. Space is cold because it has almost no matter, and the tiny amount it has is spread so thin that it can't hold or transfer heat effectively. But radiation complicates this picture. Radiation from stars does travel through space. Our Sun pumps out about 3.8 times 10 to the power of 26 watts of energy every second. That's 3.8 followed by 26 zeros. An incomprehensible amount of energy. This energy radiates outward in all directions. As it travels farther from the Sun, it spreads out over a larger area. Imagine a sphere around the Sun. Close to the Sun, the sphere is small, so the Sun's energy is concentrated over a small surface area. Farther out, the sphere is larger, and the same total energy is spread over a larger surface area. This is why intensity decreases with distance. It's not that the energy disappears. It's that it's spread thinner. The intensity of radiation decreases with the square of the distance. This is called the inverse square law. If you double the distance from the Sun, the intensity drops to 1/4. Triple the distance, and it drops to 1/9. At Earth's distance, about 93 million miles from the Sun, the intensity of solar radiation is about 1,366 watts per square meter. That's the solar constant, the amount of solar energy hitting each square meter of Earth's surface when the Sun is directly overhead and there's no atmosphere in the way. At Mars, about 142 million miles from the Sun, the intensity drops to about 590 watts per square meter, less than half what Earth receives. At Neptune's distance, about 2.8 billion miles, the intensity is down to about 1.5 watts per square meter. That's less than 1,000th of what Earth receives. Neptune is so far from the Sun that sunlight there is barely brighter than a full moon on Earth. Now, let's talk about different types of stars and their temperatures, because the Sun is just one example. Stars come in a wide range of sizes, masses, and temperatures. The smallest stars are red dwarfs. These are stars with less than about 40% of the Sun's mass. They burn hydrogen very slowly and very efficiently. Their surface temperatures are relatively cool for stars, about 5,000 to 7,000 degrees Fahrenheit. Cool enough that they glow red rather than yellow or white. Red dwarfs are the most common type of star in the universe. They make up about 70 to 80% of all stars. But they're so dim that none of them are visible to the naked eye from Earth. Even Proxima Centauri, the nearest star to the Sun, is a red dwarf too faint to see without a telescope. Despite being cool and dim, red dwarfs will outlive every other type of star. They burn their fuel so slowly that the smallest ones will keep shining for trillions of years, far longer than the current age of the universe. No red dwarf has ever died of old age, because the universe isn't old enough yet. On the other end of the spectrum are blue giants and supergiants. These are massive stars with 10, 20, 50, or even 100 times the mass of the Sun. They burn hydrogen incredibly fast, fusing it at prodigious rates. Their cores reach temperatures of hundreds of millions of degrees. Their surfaces are far hotter than the Sun, ranging from 20,000 to 50,000 degrees Fahrenheit, or even higher. At these temperatures, they emit most of their light in the blue and ultraviolet parts of the spectrum. They glow blue-white, intensely bright. A single blue supergiant can be as luminous as 1,000,000 suns, but they pay a price for this brilliance. They burn through their hydrogen fuel in just a few million years. Some of the most massive stars last only 1,000,000 years or less before they exhaust their fuel and explode as supernovas. Rigel, in the constellation Orion, is a blue supergiant. It's about 79 times the radius of the Sun and about 21 times as massive. Its surface temperature is about 21,000 degrees Fahrenheit, more than twice as hot as the Sun. It pumps out about 120,000 times more energy than the Sun. If you replace the Sun with Rigel, Earth would be vaporized instantly. The intense radiation would strip away our atmosphere, boil the oceans, and melt the surface. Fortunately, Rigel is about 860 light-years away, far enough that it's just a bright star in our night sky. Between red dwarfs and blue giants are stars like the Sun, called yellow dwarfs or G-type main sequence stars. The Sun is medium-sized, medium temperature, and medium brightness. Nothing special, really. Just an average star in an average galaxy. But that averageness is part of why it's suitable for life. Massive hot stars don't live long enough for complex life to evolve. Earth needed about 4 billion years to go from simple cells to complex multicellular life. A massive star burns out in a few million years. Not nearly enough time. Small, cool stars live a very long time, but they're dim. Their habitable zones, the regions where planets could have liquid water, are very close to the star. So close that planets there would be tidally locked, always showing the same face to the star. one side perpetually baked, the other perpetually frozen. Not ideal for life as we know it. Medium stars, like the Sun, hit a sweet spot. They live long enough for life to evolve, billions of years. Their habitable zones are far enough from the star that planets aren't tidally locked. And they're stable, not prone to massive flares or variations in brightness. This is one reason why finding Earth, like planets around Sun, like stars, is a focus of the search for extraterrestrial life. When stars die, the process depends on their mass. Small stars, red dwarfs, and stars like the Sun will eventually expand into red giants. The Sun will do this in about 5 billion years. As it runs out of hydrogen in its core, it will start burning hydrogen in a shell around the core. This will cause the outer layers to expand dramatically. The Sun will swell to perhaps 100 times its current radius, large enough to engulf Mercury and possibly Venus. Earth might survive, but it will be a scorched, lifeless rock. The surface temperature of a red giant is cooler than the Sun's current surface, about 5,000 degrees or less. But because the star is so much larger, its total energy output increases. The Sun as a red giant will be thousands of times more luminous than it is now. Eventually, the outer layers will drift away, forming a planetary nebula. The core will collapse into a white dwarf, a dense, hot remnant about the size of Earth, but with the mass of the Sun. A white dwarf doesn't generate energy through fusion. It's just sitting there, cooling off, radiating away its residual heat. A newly formed white dwarf can have a surface temperature of 100,000 degrees Fahrenheit or more. But it cools slowly. Over billions of years, it fades and cools, eventually becoming a black dwarf, a cold, dark cinder. No white dwarf has cooled to become a black dwarf yet, because the universe isn't old enough. Even the oldest white dwarfs are still glowing. Massive stars die more dramatically. When a massive star exhausts its hydrogen, it starts fusing helium into carbon and oxygen. Then, it fuses carbon into neon and magnesium, neon into oxygen and silicon, silicon into iron. Each stage requires higher temperatures and produces less energy. The star's core becomes layered like an onion, with different elements fusing in different shells. Iron is the end of the line. Fusing iron doesn't release energy. It absorbs energy. Once the core fills with iron, fusion stops. The core has nothing to support it against gravity. It collapses. In less than a second, a core the size of Earth collapses to a ball about 12 miles across. The density becomes so extreme that protons and electrons are crushed together, forming neutrons. The core becomes a neutron star, a ball of neutrons packed so tightly that a teaspoon of neutron star material would weigh about 1 billion tons. The collapse releases an enormous amount of gravitational potential energy. This energy blows the outer layers of the star apart in a supernova explosion. For a few weeks, a single supernova can outshine an entire galaxy. The explosion ejects heavy elements into space, seeding the galaxy with the raw materials for new stars and planets. All the elements heavier than iron in your body, the calcium in your bones, the iron in your blood, came from supernova explosions billions of years ago. You're made of stardust, literally. The neutron star left behind is incredibly hot, billions of degrees initially. But it's also incredibly small, only about 12 miles across. It radiates energy away quickly, cooling to millions of degrees within years, thousands of degrees within millions of years. Some neutron stars are pulsars, spinning rapidly and beaming radiation from their magnetic poles. If the beam sweeps across Earth, we see a pulse of radio waves or X-rays, like a lighthouse beam. The fastest pulsars spin hundreds of times per second. These are objects with more mass than the Sun, compressed into a ball the size of a small city, spinning faster than a helicopter blade. If the collapsing core is massive enough, even neutron pressure can't stop the collapse. The core keeps collapsing, crushing matter out of existence, forming a black hole. Nothing, not even light, can escape from inside a black hole's event horizon. But just outside the event horizon, matter can orbit at incredible speeds, heated to billions of degrees by friction and gravitational compression. This forms an accretion disk, a swirling disk of superheated gas glowing intensely in X-rays. The area around a black hole can be one of the hottest places in the universe, billions or even trillions of degrees. But just a short distance away, in the empty space between stars, the temperature is minus 454 degrees Fahrenheit. Hot and cold existing side by side, separated by distance and by the presence or absence of matter. If you were floating in space at Neptune's distance, you'd receive so little radiation from the Sun that you'd cool down to near the cosmic background temperature, about minus 454 degrees. The Sun would look like a bright star, but it wouldn't warm you. You'd be bathed in the faint microwave glow of the cosmic background, and you'd radiate away your own heat until you reached equilibrium with that background. You'd freeze. This brings us to another important point. Cold isn't a thing. We talk about cold as if it's a substance, something that flows from cold objects to warm objects. But that's not how it works. Cold is just the absence of heat. Heat is energy, specifically the kinetic energy of particles. When we say something is cold, we mean its particles have low kinetic energy. They're moving slowly. When we say something is hot, we mean its particles have high kinetic energy. They're moving fast. Heat flows from hot to cold because energy naturally spreads out. This is the second law of thermodynamics. Energy moves from concentrated areas to dispersed areas until everything reaches equilibrium. A hot object in contact with a cold object will transfer energy to the cold object until both are the same temperature. In space, objects radiate energy in all directions. If the object is hotter than its surroundings, it radiates more energy than it receives, so it cools down. If it's cooler than its surroundings, it receives more energy than it radiates, so it warms up. Eventually, it reaches a balance where the energy it radiates equals the energy it receives. For an object in deep space, far from any stars, the energy it receives is just the cosmic microwave background. That's why it cools to about minus 454 degrees Fahrenheit. It's in equilibrium with the background radiation. For an object near a star, the calculation is more complex. It receives radiation from the star, and it receives the cosmic background. It also radiates its own energy based on its temperature. The balance between energy received and energy radiated determines its equilibrium temperature. Earth, for example, receives energy from the Sun. It also receives a tiny amount from the cosmic background, but that's negligible compared to solar radiation. Earth radiates energy back into space as infrared radiation. The balance between incoming solar radiation and outgoing infrared radiation determines Earth's temperature. If Earth had no atmosphere, its average temperature would be about 0 degrees Fahrenheit. Cold, but not as cold as deep space. Earth's atmosphere traps some of the outgoing infrared radiation, warming the surface to an average of about 57 degrees Fahrenheit. This is the greenhouse effect, and it's why Earth is habitable. Without it, the oceans would freeze. But even with the greenhouse effect, Earth is constantly radiating heat into space. At night, when your part of Earth rotates away from the sun, you stop receiving solar radiation. The ground cools by radiating infrared energy into space. The air above the ground cools through contact with the ground. This is why nights are cooler than days. You're losing heat to space through radiation, and you're not receiving enough from the sun to compensate. Now, let's talk about interstellar space. The space between stars. This is where things get even more interesting. Interstellar space isn't completely empty. It contains a thin gas, mostly hydrogen, with trace amounts of helium and heavier elements. The density is incredibly low, typically about 1 atom per cubic centimeter, but in some regions it can be higher. In dense molecular clouds, regions where new stars are forming, the density can reach thousands or even millions of atoms per cubic centimeter. Still far less dense than any vacuum on Earth, but dense enough for the atoms to interact with each other. Let's talk about these molecular clouds in more detail, because they're some of the most interesting places in the galaxy when it comes to temperature. Molecular clouds are vast regions of space filled with gas and dust. They're called molecular clouds because the gas is cold enough for atoms to bond together into molecules. Hydrogen atoms pair up to form molecular hydrogen. Carbon and oxygen combine to form carbon monoxide. Other molecules form too: water, ammonia, methane, even complex organic molecules. These clouds are cold, typically about -420 degrees Fahrenheit, or even colder. In the densest regions, temperatures can drop to -440 degrees, just a few degrees above absolute zero. Why so cold? Because the clouds are shielded from starlight. The dust in the cloud blocks visible and ultraviolet radiation from nearby stars. Without this radiation to heat them, the gas and dust cool down by radiating away their own heat. The molecules emit infrared radiation and microwave radiation, carrying energy away. Over time, the cloud cools to just a few degrees above the cosmic background temperature. These clouds are dark. If you were inside one, you wouldn't see any stars. The dust blocks the light. You'd be surrounded by total darkness, except for the faint infrared glow of the dust itself. But despite being cold and dark, these clouds are where stars are born. Gravity is slowly pulling the gas together. In the densest regions, where the gas has accumulated, the gravitational pull becomes strong enough to overcome the internal pressure of the gas. The gas starts to collapse. As it collapses, it heats up. Gravitational potential energy converts to kinetic energy. The atoms move faster, which means higher temperature. The collapsing region, now called a protostar, gets hotter and hotter. At first, it's still too cold to glow visibly. It emits infrared radiation, detectable by infrared telescopes but not visible to the eye. As the collapse continues, the temperature rises. The core of the protostar reaches thousands of degrees, then tens of thousands, then millions. Eventually, the core gets hot enough for nuclear fusion to begin. Hydrogen starts fusing into helium, and a new star is born. The newborn star is incredibly hot, with a core temperature of millions of degrees and a surface temperature of thousands or tens of thousands of degrees. But it's surrounded by the cold, gas, and dust of the molecular cloud. The star's radiation begins to heat and push away the surrounding material. Intense ultraviolet radiation from the hot young star ionizes the gas, stripping electrons from atoms. This creates an H2 region, a bubble of hot ionized gas around the star. The temperature in an H2 region can reach 18,000 degrees Fahrenheit or higher. The gas glows brightly in visible light, creating beautiful nebulas like the Orion Nebula or the Eagle Nebula. But just outside the H2 region, in the parts of the molecular cloud that haven't been ionized yet, the temperature is still near absolute zero. Hot glowing gas next to freezing dark clouds, separated by a sharp boundary called an ionization front. This is another example of how temperature in space can vary dramatically over short distances. It's all about the presence or absence of matter and energy. The H2 region has matter and energy, ultraviolet radiation from the star heating the gas. The molecular cloud has matter but little energy, so it stays cold. The space between stars has neither matter nor energy, so it settles to the background temperature. Another fascinating temperature environment is planetary nebulas. When a star like the Sun dies, it ejects its outer layers into space. These layers form an expanding shell of gas around the dying star. The core of the star, now a white dwarf, is incredibly hot, over 100,000 degrees Fahrenheit. It pumps out intense ultraviolet radiation. This radiation ionizes the expanding gas shell, causing it to glow. The gas itself has a temperature of about 18,000 to 50,000 degrees Fahrenheit. But the gas is extremely thin, with densities of just a few hundred to a few thousand atoms per cubic centimeter. So even though it's hot, it doesn't contain much heat. A person floating in a planetary nebula would be bathed in ultraviolet radiation from the central white dwarf. That radiation would be dangerous, potentially lethal. But the gas itself, despite being thousands of degrees, wouldn't feel hot because it's so sparse. You'd lose heat through radiation faster than you'd gain it from the hot but thin gas. You'd freeze before the gas could warm you. Supernova remnants are similar. After a massive star explodes, the ejected material expands outward at thousands of miles per second. This material slams into the surrounding interstellar gas, creating a shock wave. The shock wave heats the gas to millions or even billions of degrees. The gas emits X-rays, a sign of extreme temperatures. The Crab Nebula, the remnant of a supernova observed in the year 1054, has gas temperatures reaching several million degrees. But again, the density is low. The hot gas can't transfer much heat to anything because there's so little of it. Temperature and heat are different things. Temperature measures the average kinetic energy of particles. Heat measures the total energy. You can have high temperature with low heat if the number of particles is small. This is the case in most astronomical environments. High temperatures are common, but high heat is rare because the densities are so low. These atoms have kinetic energy. They're moving. And if you measured their average kinetic energy, you could assign a temperature to the gas. In some regions of interstellar space, this temperature is surprisingly high. In the hot, ionized medium, regions where gas has been heated by supernova explosions or radiation from massive stars, temperatures can reach millions of degrees. Wait, millions of degrees? How is that possible if space is cold? Here's where you have to be careful about what temperature means. Those atoms are indeed moving very fast, so their kinetic temperature is millions of degrees. But there are so few of them that the total amount of heat energy is negligible. If you put your hand in a region of million-degree gas in space, you wouldn't burn. You wouldn't even feel warm. Why not? Because heat transfer depends not just on temperature, but on the number of particles. Heat is energy, and energy is transferred when particles collide. In a dense gas, like Earth's atmosphere, trillions of hot atoms collide with your hand every second, transferring energy. You feel this as heat. In the hot, ionized medium of space, atoms are so sparse that only a few would hit your hand each second. Each collision transfers energy, but so few collisions occur that the total energy transferred is tiny. You'd lose more heat through radiation than you'd gain from the gas. You'd still freeze. This is one of the most counterintuitive aspects of temperature. High temperature doesn't always mean something feels hot. It depends on density. A single atom moving at 1,000,000 meters per second has a kinetic temperature of millions of degrees. But one atom can't burn you because it can't transfer enough energy. 1 billion atoms moving at the same speed, a dense gas at millions of degrees, absolutely can burn you because the sheer number of collisions transfers enormous amounts of energy. Temperature measures the average kinetic energy per particle. Heat measures the total energy. Space can have regions with high temperature but low heat because the density is so low. The Sun, on the other hand, has both high temperature and high heat because it has enormous density. Let's look at some specific examples of temperature in the solar system. Mercury, the closest planet to the Sun, experiences extreme temperature swings. On the side facing the Sun, temperatures can reach 800 degrees Fahrenheit, hot enough to melt lead. On the night side, temperatures drop to minus 290 degrees. Mercury has almost no atmosphere, so there's nothing to transport heat from the day side to the night side. Each side reaches equilibrium with the radiation it receives. The day side bakes under intense solar radiation. The night side radiates heat into space and cools to near the background temperature. Venus, the second planet, is actually hotter than Mercury, despite being farther from the Sun. Surface temperatures on Venus average about 864 degrees Fahrenheit. This is because Venus has a thick atmosphere of carbon dioxide, a powerful greenhouse gas. The atmosphere traps heat so effectively that Venus maintains a nearly uniform temperature day and night. The greenhouse effect on Venus is so strong that it overwhelms the difference in solar radiation between day and night. Earth, as we've discussed, maintains a moderate temperature thanks to a much milder greenhouse effect. Our atmosphere keeps us warm enough for liquid water, but not so warm that the oceans boil. Mars has a very thin atmosphere, about 1% the pressure of Earth's atmosphere. With so little atmosphere, Mars can't trap much heat. Surface temperatures average about minus 80 degrees Fahrenheit. Near the equator in summer, temperatures can reach a comfortable 70 degrees during the day. But at night, or near the poles, temperatures plunge to minus 225 degrees or colder. Without a thick atmosphere to retain heat, Mars quickly radiates away any warmth it receives from the Sun. The gas giant planets, Jupiter, Saturn, Uranus, and Neptune, have their own internal heat sources. They're still slowly contracting from their formation, and this contraction releases gravitational potential energy as heat. Jupiter, for example, radiates about 1.7 times as much energy as it receives from the Sun. Saturn radiates about 1.8 times as much. This internal heat keeps them warmer than they would be from sunlight alone. But warmer is relative. The cloud tops of these planets are still brutally cold, ranging from about -230 degrees on Jupiter to -370 degrees on Neptune. Their interiors are warmer, potentially reaching tens of thousands of degrees deep inside, where pressure is extreme. But their surfaces, the cloud layers we can see, are frozen. Pluto, a dwarf planet in the outer solar system, is even colder. Surface temperatures average about -387 degrees Fahrenheit. At this distance from the Sun, about 3.7 billion miles, solar radiation is so weak that Pluto receives almost no heat. It sits in the cold, dark, barely warmer than the cosmic background. The coldest natural place we've measured in the solar system is in permanently shadowed craters near the poles of the Moon and Mercury. These craters never receive sunlight because of the very small tilt of these worlds. The crater floors are in permanent shadow, and they can't see the warm sky. They only see the cold of space. Temperatures in these craters can drop to about -413 degrees Fahrenheit, colder than Pluto because they're in shadow, protected from even the tiny amount of sunlight that warms Pluto. In these craters, water ice can remain frozen for billions of years. These are some of the coldest places in the solar system, approaching the background temperature of space itself. Now, let's think about what happens far beyond our solar system, in the vast space between stars. The Milky Way contains a few 100 billion stars, but the distances between them are enormous. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. That's about 25 trillion miles. The space between our Sun and Proxima Centauri is nearly empty. There's the occasional atom of hydrogen, maybe some dust grains, and the faint radiation from distant stars and the cosmic background. An object floating in that space, halfway between our Sun and Proxima Centauri, would receive almost no radiation. Both stars would appear as bright points of light, brighter than other stars, but not bright enough to provide meaningful heat. The object would cool to the background temperature, about -454 degrees Fahrenheit. It would sit there in the dark and the cold for billions of years unless something disturbed it. This is the nature of most of the universe. Cold, dark, empty. The stars are islands of heat and light in an ocean of cold and darkness. They're so far apart that their influence barely reaches across the void. Even our own galaxy, with its hundreds of billions of stars, is mostly empty space. If you could remove all the stars, all the gas, all the dust, you'd be left with a volume of space about 100,000 light-years across that's almost completely empty except for the faint glow of the cosmic microwave background. Let's zoom out further. Between galaxies, the situation is even more extreme. The Milky Way and Andromeda, our nearest large galactic neighbor, are about 2.5 million light-years apart. That's about 15 billion trillion miles. The space between them, intergalactic space, is even emptier than interstellar space. The density drops to about 1 atom per cubic meter. That's 1 atom in a volume the size of a large washing machine. At this density, atoms almost never collide with each other. Each atom is alone, drifting through the void, maybe encountering another atom once every few thousand years. The temperature of intergalactic space, measured by the kinetic energy of these sparse atoms, can vary. In some regions, it's close to the cosmic background temperature. In other regions, particularly in galaxy clusters, where dark matter concentrations create gravitational heating, temperatures can reach millions of degrees. But again, this is kinetic temperature. The actual heat content is negligible because the density is so low. The cosmic microwave background provides a floor temperature for the universe. No matter how far you go from any stars, you can't get colder than this background unless you actively remove energy. And scientists have done exactly that in laboratories on Earth. Using techniques like laser cooling and evaporative cooling, physicists have cooled atoms to temperatures within a billionth of a degree above absolute zero. These are the coldest temperatures ever achieved anywhere in the universe, as far as we know. Colder than the depths of intergalactic space. Colder than the coldest molecular clouds. Colder than anything natural. Why can't we reach absolute zero? The third law of thermodynamics states that you can't reach absolute zero in a finite number of steps. You can get arbitrarily close, but you can never quite get there. This is partly because of quantum mechanics. Even at absolute zero, particles still have a minimum amount of energy called zero-point energy. They can't stop moving completely because the Heisenberg uncertainty principle forbids it. If a particle had exactly zero motion, you'd know its momentum exactly, which would mean you couldn't know its position at all. The particle would be smeared out over all of space. Quantum mechanics requires that particles always retain some minimum motion, some zero-point energy, even at the coldest possible temperature. So absolute zero is a theoretical limit, approached but never quite reached. Let's return to our original question with everything we now know. Why is space cold when stars are hot? Space is cold because temperature is a property of matter, and space has almost no matter. The few atoms that do exist in space are spread so thin that they can't effectively transfer heat. Stars are hot because they contain enormous amounts of matter packed densely together and energized by nuclear fusion. That heat doesn't spread to fill the space around stars because there's nothing to carry it. Heat transfer in a vacuum occurs only through radiation, and radiation spreads out over distance, becoming weaker and weaker the farther you go from the source. By the time you're a few 100 million miles from a star, its radiation is too weak to keep you warm. You radiate your own heat into the void, and eventually you cool to the background temperature of the universe. This is the reality of space. It's not that space is filled with cold. It's that space is filled with nothing, and nothing has no temperature. The universe is mostly emptiness. The stars, the galaxies, the planets, all the matter we can see, all of it together, makes up less than 5% of the universe's total energy content. The rest is dark matter and dark energy, substances we don't fully understand. But even if you add in dark matter, most of the universe is still empty space. The distances between objects are so vast that they might as well be alone in the universe. And in that emptiness, there's no warmth, no heat, just the faint afterglow of the Big Bang and the radiation from distant stars, spread so thin that it barely registers. This emptiness is part of what makes the universe so strange and so beautiful. Stars shine brilliantly against the darkness, but they're tiny islands in an infinite ocean. Earth sits in one small, warm bubble around one ordinary star. Outside that bubble, in every direction, the cold and the dark stretch on for billions of light years. We're warm because we're close to a star, and because we have an atmosphere to trap that warmth. But we're surrounded by cold. The moon, just 250,000 miles away, has no atmosphere. Its surface bakes at 250 degrees in sunlight and freezes at -240 degrees in shadow. That's the reality of space. Extreme heat in direct radiation, extreme cold everywhere else. The contradiction isn't really a contradiction at all. It's just the consequence of how heat works in a vacuum. Without matter to carry heat, warmth doesn't spread. It radiates outward and dissipates. Stars are hot, but their heat doesn't fill space. It streams away as radiation, weakening with distance until it's indistinguishable from the background. And that background, the cosmic microwave background, is the temperature of the universe itself. About -454 degrees Fahrenheit. Just a few degrees above absolute zero. The coldest possible temperature. This is the baseline temperature of reality, the temperature of nothing, the temperature of the void. Everything else, every star, every planet, every warm object, is a temporary exception. Heat is rare in the universe. Cold is the default. We live on a warm island in a cold ocean, warmed by a nuclear furnace 93 million miles away, insulated by a thin layer of atmosphere. Step outside that protection, and you'd freeze. Not because space is actively cold, but because there's nothing to keep you warm. Your body would radiate heat into the void, and without an atmosphere to trap it or carry it away, you'd cool until you reached equilibrium with the background. -454 degrees. The temperature of nothing. That's space. Not filled with cold, but filled with nothing. And nothing, as it turns out, is very, very cold. The question we started with, why is space cold when stars are hot, assumes that heat from stars should fill space. But space doesn't work that way. Heat doesn't fill space because there's nothing to fill. Radiation crosses space, carrying energy, but unless that radiation is absorbed by matter, it doesn't create heat. It just passes through, heading outward into the infinite darkness. Stars burn bright and hot, pumping out inconceivable amounts of energy. But that energy spreads thin very quickly. A few light years away, it's negligible. A few dozen light years away, it's indistinguishable from any other star. A few thousand light years away, and the star is just another faint point of light in the sky. The universe is vast, beyond comprehension. The Milky Way alone is 100,000 light years across. Light, the fastest thing in the universe, takes 100,000 years to cross it. And the Milky Way is just one of hundreds of billions of galaxies. Most of that space, the space between stars, between galaxies, is cold and dark and empty. The stars are anomalies, brief flickers of heat and light in the endless cold. Our sun has been burning for about 4.6 billion years. It will burn for another 5 billion or so before it exhausts its fuel. 10 billion years total, a long time by human standards. But the universe is nearly 14 billion years old, and it will exist for trillions of years more. Eventually, all the stars will burn out. The universe will be left with dead remnants, white dwarfs, neutron stars, black holes. And the temperature will drop even further as the universe continues to expand and cool. In the far future, trillions of years from now, the universe will be a cold, dark, empty place. The cosmic microwave background will have cooled to nearly absolute zero. There will be no stars, no warmth, no light. Just the cold and the dark, stretching on forever. But that's far in the future. For now, we live in the era of stars. The universe is young enough that fusion still happens, that stars still shine, that warmth still exists. We're fortunate to live in this brief window of cosmic history. A window where heat and light are still possible, where complexity can arise, where life can evolve. In a universe that's mostly cold and dark, we exist in a tiny, warm, bright pocket. That pocket exists because of nuclear fusion in the core of a star 93 million miles away. And it exists because we have an atmosphere to trap that warmth. Without the sun, Earth would freeze. Without the atmosphere, Earth would freeze even with the sun. We're here because of a delicate balance, a narrow set of conditions that allow warmth to exist on the surface of a rocky planet. That balance is rare in the universe. Most of space is cold because most of space is empty. And empty space has no way to be warm. The stars are hot because they have matter, enormous amounts of it, energized by fusion. But their heat doesn't travel far. A few 100 million miles, and it's already too weak to matter. A few light years, and it's indistinguishable from the background. Let's explore some more fascinating examples of temperature extremes in the universe. Because the range is truly staggering. Consider the Boomerang Nebula, located about 5,000 light-years from Earth. This is a cloud of gas ejected by a dying star, and it holds the record for the coldest natural place we've ever measured in the universe. The temperature there is about minus 458 degrees Fahrenheit, or about 1 Kelvin. That's colder than the cosmic microwave background. How is that possible? The gas in the Boomerang Nebula is expanding very rapidly, about 391,000 miles per hour. When a gas expands, it cools. This is basic thermodynamics, the principle behind refrigerators and air conditioners. The rapid expansion of the gas in the Boomerang Nebula has cooled it below the temperature of the surrounding space. It won't stay this cold forever. Eventually, the expansion will slow down, and the nebula will warm up as it absorbs radiation from the cosmic microwave background. But for now, it's the coldest natural place we know of. On the opposite extreme, consider the temperatures inside a particle accelerator like the Large Hadron Collider. When protons collide at nearly the speed of light in the LHC, they create tiny fireballs of quark-gluon plasma. These fireballs have temperatures reaching about 9 trillion degrees Fahrenheit. That's about 100,000 times hotter than the core of the Sun. It's the hottest temperature ever created by humans, and possibly the hottest temperature anywhere in the universe since shortly after the Big Bang. These temperatures only exist for a fraction of a second, in a region smaller than a proton. But for that brief moment, we recreate conditions that haven't existed naturally in the universe for nearly 14 billion years. The quark-gluon plasma is a state of matter where protons and neutrons break down into their constituent quarks and gluons. This is thought to be what filled the universe when it was less than a millionth of a second old. By studying this plasma, physicists learn about the fundamental forces and particles that govern reality. Another temperature extreme occurs in the accretion disks around black holes, particularly supermassive black holes at the centers of galaxies. As matter spirals into the black hole, friction and compression heat it to billions of degrees. The inner regions of the disk, closest to the event horizon, can reach temperatures of trillions of degrees. At these temperatures, matter exists as a plasma of individual particles, electrons, protons, ions, all stripped of their atomic structure. The particles move at relativistic speeds, significant fractions of the speed of light. They emit intense X-rays and gamma rays. The radiation from these accretion disks is so intense that it can affect the entire galaxy. It can heat gas in the galaxy to millions of degrees, preventing it from cooling and forming new stars. This is called AGN feedback, where AGN stands for active galactic nucleus. It's one of the mechanisms that regulates star formation in galaxies. Without AGN feedback, galaxies would form stars too quickly and would have exhausted their gas supplies billions of years ago. The heating from the central black hole balances the cooling of gas, maintaining an equilibrium that allows galaxies to continue forming stars at a steady rate over billions of years. Now let's think about temperature in the context of the entire universe's history. The universe started hot, incredibly hot. In the first moments after the Big Bang, temperatures were so high that we can barely describe them. At 1 second after the Big Bang, the temperature of the universe was about 18 billion degrees Fahrenheit. Everything was a soup of fundamental particles, quarks, gluons, electrons, neutrinos, photons. No atoms could form because it was too hot. Any atoms that tried to form would be instantly ripped apart by energetic collisions. As the universe expanded, it cooled. By 3 minutes after the Big Bang, the temperature had dropped to about 1 billion degrees Fahrenheit, cool enough for protons and neutrons to stick together, forming the first atomic nuclei. This is when the first helium and deuterium formed, in a process called Big Bang nucleosynthesis. About 25% of the universe's hydrogen fused into helium during this brief period. The rest remained as hydrogen. This ratio, 3/4 hydrogen, 1/4 helium, is what we observe in the oldest stars and gas clouds. It's one of the key pieces of evidence for the Big Bang theory. By 380,000 years after the Big Bang, the temperature had dropped to about 5,400 degrees Fahrenheit, cool enough for electrons and nuclei to combine into neutral atoms. This is the recombination we discussed earlier. The universe went from opaque to transparent, and the photons from that era are what we now detect as the cosmic microwave background. As the universe continued expanding, it continued cooling. By a few 100 million years after the Big Bang, the temperature had dropped enough for the first stars to form. These first stars were different from stars today. They formed from gas that was pure hydrogen and helium, with no heavier elements. We call them population 3 stars, and none of them exist today. They all died long ago. They were probably very massive and very hot, living fast and dying young in supernova explosions. Those explosions seeded the universe with the first heavy elements: carbon, oxygen, silicon, iron. Later, generations of stars incorporated these elements, and eventually, after billions of years of stellar evolution, enough heavy elements accumulated to allow rocky planets to form. Today, nearly 14 billion years after the Big Bang, the average temperature of the universe is about -454 degrees Fahrenheit. the temperature of the cosmic microwave background, the universe has cooled by a factor of thousands since the Big Bang. And it will continue cooling forever, assuming current cosmological models are correct. The expansion of the universe is accelerating, driven by something called dark energy. We don't know what dark energy is, but we can measure its effects. It's causing the expansion of space to speed up, stretching the wavelengths of the cosmic microwave background photons even more. As the wavelengths stretch, the temperature drops. In the far future, the cosmic microwave background will cool to a fraction of a degree above absolute zero. The universe will become a cold, dark, empty place. All the stars will have burned out. Black holes will evaporate through Hawking radiation, a process so slow it takes something like 10 to the power of 100 years. That's a 1, followed by 100 zeros, an incomprehensible amount of time. Eventually, all that will remain is a diffuse soup of photons and particles spread across an ever-expanding space, cooled to nearly absolute zero. This is called the heat death of the universe, and it's the likely ultimate fate of everything. But that's so far in the future that it's almost meaningless to think about. Trillions of trillions of trillions of years from now. For now, we live in an era where stars still shine, where warmth still exists, where the universe is vibrant and active. Let's return to the original question with all this context. Why is space cold when stars are hot? We've covered a lot of ground, but the answer comes down to a few key principles. First, temperature is a property of matter, not of space. Empty space has no particles, so it can't have a temperature in the traditional sense. When we say space has a temperature, we're really talking about the cosmic microwave background radiation filling space. Second, heat transfer in a vacuum can only occur through radiation. Conduction and convection require a medium, and space has no medium. Radiation spreads out and weakens with distance according to the inverse square law. Third, the density of matter in space is incredibly low. Even in regions with high kinetic temperatures, the low density means the total heat content is negligible. You can't feel heat from a gas that's too thin to transfer energy effectively. Fourth, stars are localized sources of heat. They generate enormous amounts of energy through fusion, but that energy radiates outward and dissipates. A few 100 million miles away, the radiation is already weak. A few light years away, it's indistinguishable from other stars. The heat doesn't fill space because there's nothing to fill. Fifth, the cosmic microwave background provides a floor temperature for the universe, about -454 degrees Fahrenheit. Any object in deep space, far from stars, will eventually cool to this temperature as it radiates away its heat and absorbs the faint background radiation. Put all these principles together, and you understand why space is cold. It's not filled with cold. It's filled with nothing. And nothing has no temperature except what's imposed by the cosmic background. The stars are hot, but they're tiny islands in a vast ocean of emptiness. Their heat radiates away and gets lost in the infinite dark. This is the nature of the universe. Isolated pockets of heat in an expanding, cooling cosmos. And we're fortunate to live in one of those pockets, warmed by a star, protected by an atmosphere, existing in the narrow window of cosmic history, when warmth and complexity are still possible. Let me give you one more example to drive this home. Imagine you're an astronaut on a spacewalk, floating in low Earth orbit. You're about 250 miles above Earth's surface, in the thermosphere. The sparse atoms of the thermosphere around you have temperatures of thousands of degrees. But you don't feel that heat because the density is so low. Below you, Earth reflects sunlight and emits infrared radiation. If you're over the day side of Earth, you receive reflected sunlight and infrared from the warm surface. This keeps you warmer than you would be in deep space. On the night side, you receive much less radiation from Earth, just the infrared glow from the still warm surface. Above you, in every direction, is space, cold and dark, except for the stars. The sun, if it's in view, is blasting you with about 1,366 watts per square meter of radiation. Your spacesuit absorbs some of this, reflects some, and heats up. You have to actively cool yourself with the suit's thermal control system. If the sun is behind Earth, blocked from view, you stop receiving that radiation. Your suit cools as it radiates heat into space. The temperature on the sun-facing side of your suit might be 250 degrees. The temperature on the shaded side might be minus 200 degrees. A difference of 450 degrees across a few inches. This is what space is like. Temperature varies wildly depending on exposure to radiation. There's no air to smooth things out, no convection to distribute heat evenly. Just raw radiation and the slow process of radiating your own heat away. The International Space Station manages these temperature extremes with careful engineering. The station orbits with specific orientations to balance solar heating. Large radiator panels extend from the main structure, glowing in infrared as they dump excess heat. Inside, the station maintains a comfortable temperature of about 68 to 73 degrees Fahrenheit. The walls are insulated, keeping the interior separate from the temperature extremes outside. But maintaining this comfortable environment requires constant active systems. Pumps circulate coolant through loops that run throughout the station. The coolant picks up heat from electronics, experiments, and humans. It carries that heat to the radiators, where it's radiated into space. If these systems fail, the station would quickly become uninhabitable. Too hot from solar radiation and internal heat sources, or too cold if the heating systems shut down. This is the challenge of living in space. There's no natural temperature regulation, no atmosphere to buffer extremes. Everything has to be actively managed. When humans eventually travel to Mars or establish bases on the Moon, they'll face similar challenges. Buildings will need thick insulation, active heating and cooling, and careful design to minimize heat loss and heat gain. On Mars, with its thin atmosphere, dust storms can actually affect temperature. The dust suspended in the air absorbs sunlight and emits infrared radiation. During a major dust storm, the atmosphere warms up and surface temperatures become slightly more moderate. But when the dust settles, temperatures swing more wildly. On the Moon, there's no atmosphere at all, so no moderating effect. Temperature swings from plus 253 degrees to minus 243 degrees. Lunar bases will probably be built underground, buried under meters of regolith for insulation. The regolith acts as thermal mass, absorbing heat when the surface is hot and releasing it when the surface is cold. This dampens the temperature swings, making the underground environment more stable. It also provides protection from radiation, which is another hazard in space. Without an atmosphere or magnetic field, the lunar surface is bathed in cosmic rays and solar radiation. Underground habitats solve both the temperature problem and the radiation problem. The same principle would apply to Mars bases, asteroid habitats, or bases anywhere without a substantial atmosphere. Go underground. Use the regolith or rock as insulation and radiation shielding, and create a stable thermal environment. Humans are fragile. We require a very narrow range of temperatures to survive. Too cold, and we freeze. Too hot, and we overheat. We evolved on a planet with a thick atmosphere that regulates temperature. In space, we have to recreate that regulation artificially. And that requires understanding heat transfer, radiation, insulation, and all the principles we've been discussing. The coldness of space isn't an obstacle, it's just a characteristic we have to account for. With proper engineering, we can create warm environments anywhere, but it requires energy, materials, and constant active management. There's no free lunch in space. Every bit of warmth has to be generated and carefully preserved. This brings us back to Earth and how fortunate we are. Our planet sits in the habitable zone of our star, the region where temperatures allow liquid water. We have an atmosphere that traps heat and moderates temperature swings. We have a magnetic field that deflects harmful radiation. We have a water cycle that distributes heat around the planet. Oceans absorb heat in the tropics and release it at higher latitudes. Atmospheric circulation, wind, and weather patterns move heat from warm regions to cold regions. All of this creates a relatively stable climate where life can thrive. Remove any one of these factors, the atmosphere, the magnetic field, the oceans, the distance from the sun, and Earth becomes uninhabitable. Too close to the sun, and we'd be like Venus. A runaway greenhouse effect, boiling the oceans away and leaving a scorched hellscape. Too far from the sun, and we'd be like Mars. A frozen desert with a thin atmosphere, most of the water locked up as ice. We're in the sweet spot. And that sweet spot exists because of a delicate balance of factors. Star type, orbital distance, planet size, atmospheric composition, magnetic field strength. Change any of them significantly, and you lose the balance. This is why the search for habitable planets focuses on Earth-like worlds. Rocky planets similar in size to Earth, orbiting in the habitable zone of sun-like stars. These are the worlds most likely to have the right conditions for life as we know it. And even among those worlds, most won't be habitable. Maybe they don't have an atmosphere. Maybe they're tidally locked to their star. Maybe they don't have a magnetic field. Maybe they're geologically dead and can't recycle nutrients. Habitable worlds are rare. Earth might be 1 in a billion or 1 in a trillion. We don't know yet. But we know we're lucky to be here. Lucky to have a warm planet in a cold universe. Lucky to have an atmosphere that keeps us comfortable. Lucky to have a star that's stable and long-lived. And lucky to have the intelligence to understand all of this. To figure out why space is cold and stars are hot. To understand heat transfer and radiation and temperature. To build machines that protect us in the vacuum of space. To dream of exploring beyond our warm little island and venturing into the cold, dark. We've come a long way in our understanding. A few hundred years ago, people didn't even know space existed. They thought the sky was a solid dome with stars attached to it. They didn't know about the vacuum, about radiation, about temperature and heat. Today, we've sent probes to every planet in our solar system. We've landed on Mars, driven rovers across its surface. We've sent humans to the moon and brought them back. We've built a permanent outpost in orbit, the International Space Station. We've measured the temperature of the cosmic microwave background to incredible precision. We've detected gravitational waves from colliding black holes billions of light years away. We've photographed the shadow of a black hole. We've discovered thousands of planets orbiting other stars. All of this in just a few decades. Imagine what we'll know in another 100 years, in another 1,000. We're just beginning to explore the universe. And every discovery raises new questions. Dark matter, dark energy, the nature of space and time, the origin of the universe, the possibility of life elsewhere. We have so much left to learn. But we've already learned something profound. The universe is mostly cold, dark, and empty. Heat is rare. Life is rare. Warmth is precious. And we shouldn't take it for granted. Let's consider one final fascinating aspect of temperature in space, something that brings together everything we've discussed. The James Webb Space Telescope, humanity's most powerful space observatory. This telescope operates at incredibly cold temperatures. Its instruments are cooled to about -397 degrees Fahrenheit, just 40 degrees above absolute zero. Why so cold? Because the telescope observes in infrared wavelengths. Infrared radiation is heat radiation. Every warm object emits infrared. If the telescope's instruments were warm, they'd be glowing brightly in infrared, drowning out the faint infrared signals from distant galaxies. It would be like trying to observe faint stars in daylight. Your own brightness overwhelms what you're trying to see. So the instruments have to be cold. Incredibly cold. Colder than anywhere on Earth. Colder than the coldest natural place in the solar system. The telescope achieves this temperature through a combination of passive and active cooling. A massive sun shield, the size of a tennis court, blocks radiation from the sun, Earth, and Moon. This sun shield is made of 5 layers of thin material, each layer reflecting most of the radiation it receives. The layers are spaced apart so that heat can radiate away between them. The result is that the sun-facing side of the sun shield reaches about 200 degrees Fahrenheit. But the shaded side, where the instruments are, cools to about -390 degrees. Even this isn't cold enough for some instruments. The mid-infrared instrument needs to be even colder, so it has an active cooling system, a cryocooler that pumps heat away mechanically. This brings it down to about -448 degrees, just a few degrees above absolute zero. At this temperature, the instrument barely emits any infrared radiation. It can detect the faint infrared glow from the first galaxies that formed after the Big Bang. Galaxies so distant, their light has been traveling for over 13 billion years. This is engineering at its finest. Creating and maintaining extreme cold in an environment where the sun's radiation is intense. Managing temperature gradients across the spacecraft, keeping some parts warm while others stay frozen. It requires precise thermal design, exotic materials, and constant monitoring. The fact that we can build such a thing, launch it into space, and have it work flawlessly demonstrates how well we understand heat transfer, radiation, and temperature. We've taken the principles of thermodynamics and applied them to create an instrument that can peer back in time to the earliest moments of cosmic history. An instrument that operates at temperatures colder than deep space itself, shielded from the warmth of the sun by layers of reflective film. This is what understanding temperature allows us to do. Not just explain why space is cold and stars are hot, but engineer solutions to explore the universe in ways our ancestors couldn't imagine. Now, think about the cosmic irony here. To observe the hottest, most energetic events in the early universe, supernovae, quasars, the formation of the first stars, we build an instrument that operates at nearly absolute zero. The coldest human-made object in the solar system, studying the hottest events in cosmic history. Heat and cold, separated by billions of years and billions of light years, connected by light. The infrared photons that left those early hot galaxies have been traveling through cold, empty space for over 13 billion years. They've been stretched by the expansion of the universe, redshifted from visible light into infrared. They arrive at our telescope as faint whispers of ancient heat, and we capture them with an instrument colder than the space they traveled through. There's something poetic about that. The universe cooling over time, from the intense heat of the Big Bang to the frigid emptiness of today. And us, sitting in this brief, warm period, studying the past heat and the future cold, trying to understand our place in the thermal history of the cosmos. This understanding has practical applications too. Every spacecraft we build has to manage temperature. Satellites, probes, landers, rovers, all of them face the challenge of operating in an environment with no atmosphere. They can't rely on air for cooling or insulation. Everything has to be designed from first principles, using radiation, insulation, and sometimes active systems. Mars rovers, for example, have to survive nights that drop to -100 degrees Fahrenheit or colder. They use radioisotope heater units, small pellets of radioactive material that produce heat through decay. The heat keeps the electronics warm enough to function. During the day, when solar panels generate power, the rovers use that power to run heaters as needed. Without these systems, the electronics would freeze solid and stop working. The batteries would die. The rover would become a lifeless piece of metal. Venus probes face the opposite problem. The surface of Venus is about 864 degrees Fahrenheit, hot enough to melt lead. Any probe landing on Venus has to be built to withstand this heat. And it has to actively cool its electronics, because they can't function at that temperature. The Soviet Venera probes that landed on Venus in the 1970s and 80s used insulation and refrigeration systems. Even then, they only survived for about an hour or two before the heat overwhelmed them. The electronics failed, the batteries died, and the probes went silent. Designing for extreme temperatures is one of the biggest challenges in space exploration. It requires understanding heat transfer at a fundamental level and applying that understanding creatively. And it's not just spacecraft. Future space habitats, whether on the Moon, Mars, or in orbit, will need sophisticated thermal control systems. Humans generate heat through metabolism. Electronics generate heat. Life support systems generate heat. All of this heat has to be managed. In an airless environment, it can't just convect away. It has to be actively pumped to radiators and radiated into space. This is why designing a space habitat is so complex. You're creating a bubble of warmth in a cold environment, and you have to maintain that bubble indefinitely. Any failure in the thermal control system could be catastrophic. If the heating system fails, the habitat freezes. If the cooling system fails, the habitat overheats. There's no margin for error. This is the reality of living in space. It's not just about having air to breathe and food to eat. It's about managing temperature, maintaining warmth in a cold universe, and doing it reliably, day after day, for years or decades. As we look to the future, to permanent settlements beyond Earth, this understanding becomes critical. We'll be creating islands of warmth in the cosmic cold. Little pockets of Earth-like conditions on worlds that are fundamentally hostile. And it's possible because we understand heat, radiation, and temperature. Because we know why space is cold and how to create warmth where there is none. Think about what this means. Humans evolved on one planet, Earth, in conditions that are incredibly rare in the universe. Narrow temperature range, breathable atmosphere, liquid water, protective magnetic field. Everything aligned perfectly. And now we're taking the principles that govern temperature and heat and using them to create Earth-like conditions elsewhere. On Mars, where the average temperature is -80 degrees. On the Moon, where temperatures swing by 500 degrees between day and night. In orbit, where one side of a spacecraft bakes at 250 degrees and the other freezes at -250. We're bringing warmth to the cold, creating habitable environments in uninhabitable places. It's one of the most ambitious things our species has ever attempted, and it's built on understanding simple principles: heat transfer, radiation, conduction, convection, temperature as kinetic energy of particles, the vacuum as an insulator. These are the tools we use to survive in space, to push beyond our warm little planet and explore the cold, dark universe. And every time we do it successfully, every rover that survives a Martian night, every telescope that operates at near absolute zero, every astronaut who returns safely from a spacewalk, it's a validation of our understanding. We got it right. We figured out how temperature works in space, and we're using that knowledge to explore. This is what science does. It takes questions like, why is space cold when stars are hot, and turns them into opportunities? Opportunities to build, to explore, to understand. The question isn't just answered, it's applied. And that application opens up the universe. Space is cold because heat is local, tied to matter, confined to specific places. And space, by definition, is the absence of those places. It's the void between them. And the void has no temperature except the faint echo of the Big Bang. That echo, the cosmic microwave background, is what gives space its temperature. It's the remnant heat of the universe's birth, stretched and cooled by 14 billion years of expansion. It's everywhere, filling every cubic centimeter of space with a faint glow of microwave radiation. And that glow is cold. -454 degrees Fahrenheit. That's the temperature of the universe. The temperature of space. The temperature of nothing. Stars burn hot, but they're islands. Space is cold because it's an ocean. And oceans, when they're empty, take on the temperature of their surroundings. In space, the surroundings are the cosmic background. Cold, ancient, and unchanging. That's why space is cold when stars are hot. Not because of distance, though distance matters. Not because of vacuum, though vacuum matters too. But because temperature is a property of matter, and space is the absence of matter. The stars have matter, so they can be hot. Space doesn't, so it's cold. Simple as that. Thanks for staying with me through this journey into one of the most fundamental contradictions in the universe. A contradiction that, as it turns out, isn't a contradiction at all. It's just physics. The same physics that governs everything from the warmth of sunlight on your face to the frozen darkness between galaxies. And now you understand it.